We've been doing several lessons now where we looked at the shape of molecules, but in those lessons we were looking at the shape of bonds and lone pairs. Now we want to look at molecules from a different perspective and look at just the shape of the molecule itself, looking at the angles of the bonds between the atoms in the molecule. Okay, so we have been working on the shape of things. Okay, we're talking about types of bonding. We started out in this unit talking about ionic bonding and how you move electrons around to create simple ionic bonds where you have a binary compound where you have just two elements, a metal and a non-metal. For example, the metal gives up electrons, the non-metal gains electrons. And then we talked about covalent bonding where electrons are actually shared. And we've been spending a lot of time talking about how that sharing takes place. So in this lesson we're going to wrap up explaining how that sharing takes place. We've been looking at the shape of bonds and lone pairs and how we get to those, and how we get from the hybridized orbitals, and then when you share electrons, how that forms bonds. And we talked about how hybridized orbitals, when you put those together, okay, you share electrons by overlapping or combining two orbitals from two different atoms, you get a covalent bond. And we've been looking at, through these balloon models, how that forms these different shapes. So that's one way of thinking about it, okay? There's a different category. The last category we're going to talk about is how we figure out the shape of a molecule. So let me just tell you up front, when we're talking about the shape of a molecule, we ignore the lone pairs and the shape of the bonds. We just look at the angles between the atoms themselves, okay? Now, the lone pairs matter because they will help to shape the molecule. But the actual name of the shape and the shape we draw for the final shape of the molecule ignores the lone pairs. Let me show you how that works, okay? So let's go back to what we were doing before. Let's just look at water. That's kind of a pretty prototypical molecule to look at. And we said that when we were figuring out the shape of that, or the shape of the bonds anyway, and the shape of the lone pairs, we looked at the electron dot formulas. And we showed how those electrons are shared in a way that gives hydrogens 2 electrons, and the oxygen and almost any other atom 8 electrons in their valence level. Not in all levels, but just in the outermost energy level. We call that the valence level. And then we drew what's called a Lewis dot formula from that, where we sort of push the electrons that are shared together, or squeeze them together between the atom symbols. We get something like this. Oh, I put too many hydrogens on there. Let me erase that bottom one there. Now that's not the only way to draw this. It's just the way I chose to draw it today. It's perfectly okay to put the hydrogens on some other sides. So we could also make this a put the hydrogen up here, or we could put the hydrogen here and here, or we could do it with the hydrogens here and here. It doesn't really matter, okay? All those are perfectly okay. And those are called Lewis dot formulas, okay? So we started, this is a molecular formula. This is a sharing arrangement. We started with electron dot formulas, and then we circled the electrons. We created a sharing arrangement, and now we have a Lewis dot formula. From this, we were able to figure out the shape of the orbitals that we need for this bonding to take place. All lone pairs come from hybridized orbitals. Sigma bonds, single bonds, and this is a single bond because I'm sharing just 2 electrons. A single bond is a sigma bond. All single bonds are sigma bonds. And sigma bonds and lone pairs always come from hybridized orbitals. So what we have here, I can look at this formula, this Lewis dot formula, and see that I need 4 hybridized orbitals. And the only hybridization that gives us 4 hybridized orbitals is called sp3. So the shape of an sp3, if this is oxygen is the center of this atom, we have an sp3 hybridized orbital that goes up in that direction. We've got one that goes in this direction. We've got one that goes coming out toward you. It's kind of hard to see that when you're drawing this on a flat piece of paper, and then one back behind that, so that all of these are at 109.5 degrees apart. If I were to draw or put a needle directly to the center of each of those things, we'd have angles that are 109.5 degrees apart. Then two of these hybridized orbitals have pairs of electrons in them. They can't bond. Once you get two electrons in an orbital or a bond, basically it's done. It can't do anything else. So two of these orbitals are going to have two electrons in them, and we don't do anything else with them. They stay like that. But then the other orbitals that have just one electron in them, as I can see up here that I've got two orbitals that have just one electron in there, they're able to share that electron with something else. And what they're going to share it with is a hydrogen atom. And so what we're going to do to get the shape of this actual molecule is we're going to combine the s orbital from the hydrogen and the hybridized orbital from the oxygen. And I didn't put the electrons in there, so let's put an electron here and one here, so there's an electron available to share. You can see that up here in the electron dot formula, but now I put that electron in there. So they're going to share, and then we're going to put it together into a molecular shape, or at least a shape of the bonds and lone pairs in a molecular arrangement anyway. Okay, so here's the oxygen center, here's a hydrogen center, here's another hydrogen center, and so when I overlap and combine this orbital with this one, we get a shape that's more of a hot dog wiener sort of shape. And the same thing here. And the lone pairs still stay in that same hybridized orbital shape. They don't change anything. Okay. Well, now we've combined this orbital and this orbital, and the electrons are now shared together. So I've got two electrons in this orbital and two electrons in this orbital, and we call this a sigma bond. Okay, that's the symbol, the Greek letter sigma, or at least that's my representation of it. And these are lone pairs over here. They're called lone pairs because they're alone. They're not combining with anything. Okay? That's what we've been doing so far. All right? What we're going to do today is to figure out how to determine the shape of the molecule itself, not looking at the shape of the bonds and the lone pairs. All right? The system for that works like this. We're going to go up here to our Lewis dot formula, and we're going to count the sets of electrons around the atom we are interested in. Well, in these small molecules, the atom we are interested in is the one around which the molecule's shape is built. And that would be the oxygen. It's kind of like the center of everything. Okay? It's the oxygen that determines the shape of this molecule because it's the one in the center. Now, really large and complex molecules, you'll have a lot of centers, okay? And you'll have to figure out a lot more about the shape. But in here, we're just doing with simple ones, and we're going to look at how this simple molecule is shaped, and it's all based on the shape that's governed by this oxygen, okay? So I'm going to put an oxygen right down here, and I'm going to ask myself, how many sets of electrons do I have? And now sets in this context are a little different. In this context, a set can be a lone pair. And a set, it can also be and is also all the electrons shared between two atoms. So in this case, I've only got two electrons shared between these two atoms, but I could have 4 or 6. So a set is all the electrons shared between any two atoms and also lone pairs. And so by that definition, then I have 4 sets of electrons. Okay? What I want is a 3-dimensional arrangement, a geometry that gets 4 sets of electrons as far apart as I can get them in 3-dimensional space. And as we can see from this shape here, that's called a tetrahedral, where one's going up like this, one is 109.5 degrees, this is 109.5 degrees from these two, that's 109.5 degrees from all the others. And so if I'm just going to show just those angles, as I would if I were doing it in a geometry class, then I'd have an angle going up like that and an angle coming out here at 109.5 degrees. And then to get the next one at 109.5 degrees, I need one that's swinging up toward you, like I'm turning this pencil up toward you, okay, or this marker. And to show that, the traditional way to do that in chemistry is to make a triangle. And that represents an angle that's pointing sort of away from the paper and up toward you, okay? And then to show one that's going back behind the paper, we use a dotted line. Okay, so that one's going back behind the paper. Okay? Now all of these are 109.5 degrees apart. Okay, so it's just 3 dimensions. What I'm going to first draw is I'm going to show these electrons that are around that central atom here. Okay, and there are 4 sets of electrons around the central atom. So in each of these angles is showing the angle between each of the sets of electrons, much like with this set of hybridized orbitals there. For the record, the angle from here to here is 109.5 degrees. Okay. How did I figure out how to draw 109.5 degrees? Well, 90 degrees is like this. Okay, 120 degrees is about like that. And I really probably should have had that slightly higher. It's not where it's not definitely on 109.5 degrees, but it's pretty close. Okay, so it's between 90 and 120, halfway in between, basically. Okay, that's how I figured out 109.5 degrees. The next step in the process, and by the way, we said this is called a tetrahedral, so let's go ahead and call this a tetrahedral. And that's the geometry name. Okay, there used to be a commercial for Oscar Mayer hot dogs and wieners and bologna. Y'all hear that old song? It's a bologna has a first name. Y'all remember that song? Okay, well.
My bologna has a first name. It's O-S-C-A-R. My bologna has a second name. It's M-A-Y-E-R. Oh, I love to eat it every day. And if you ask me why, I'll say, 'cause Oscar Mayer has a way with B-O-L-O-G-N-A. How's that?
So these shapes have 2 names, okay, or 2 parts of the name. One is the geometry, and the other part of the name is what is the stage of this set of drawings. Okay, and this stage of the set of drawings is an electron pair shape, because we're showing the shape of the electron pairs around the atom we're interested in here, an electron pair shape. So 2 parts to the name, okay? And every one of these drawings has 2 parts to the name. The next thing I want to do, and I hope you're doing this in pencil, is to redraw this exact same drawing a second time. That's the place to start. So you're going to have an oxygen at the center, and have a leg going up like that, if you want to call it a leg coming out here like this, a leg swinging out in front, and a leg that's swinging back behind everything over here, okay? And we need our pairs of electrons on there, so I'm redrawing exactly the same drawing, okay? And what I'm going to do is I'm going to go back up and look at my Lewis dot formula up here, one of these 4, and I'm going to ask myself how many of those sets of electrons are actually shared with an atom. And I'm going to replace that many sets of electrons with the symbol for the atom. Okay, so I've got 2 sets of electrons shared with an atom, so I need to replace 2 of these sets of electrons with an atom. So I'm going to replace this one at the top and the one over here. It really doesn't matter which one you replace. Okay, they're all 109.5 degrees, so the angle won't matter. Now when you get to college, it is going to matter, because there are some shapes that we're not going to deal with in this class where it matters where you actually put the atoms. Okay, now double bonds and triple bonds are different, but as far as the angles of the bonds, it doesn't matter too much. So I need to have 2 of these angles with hydrogens on here. Okay, and then that means that 2 of these angles over here, or arms, whatever we want to call them, have lone pairs of electrons still on them. So that's kind of like an electron pair shape, but we've modified it a bit by showing what atoms go on which angles. Okay, So it's still a tetrahedral, still 4 arms or angles equally spaced, but you can't really call it an electron pair shape, so I just call it a modified electron pair shape. And I put a S on this first pairs over here. It should be just an electron pair shape. All right. Then we're going to redraw this drawing exactly as it appears there. Now, there's an important point in drawing it exactly as it appears. If you don't redraw it exactly as it appears, you're going to get your final shape wrong. I've seen it happen many, many times. Some students can do it without doing that, but most students really need this is like your training wheels on a bike till you learn to ride a bicycle without training wheels, okay? If you don't do these steps, you are most likely going to get the shape of the molecule wrong, okay? So don't take shortcuts right now. The next thing is to redraw this exact same drawing. So I've got an oxygen here, hydrogen going up here, hydrogen coming out here, 2 lone pairs. Okay. So the last step then, once you redraw it with all those angles on there, is to get rid of the lone pairs. And that's why I wanted you to do it in pencil, so you can erase the lone pairs. Okay? And you can see the shape of the molecule now. Okay? This is no longer tetrahedral. There are no longer 4 equal angles anymore. Okay? This is an uneven arrangement. That's going to become important later on when I say it's uneven. It's not important right this minute, but it will be important later on. If I get rid of lone pairs, it makes it uneven. And the really highly technical name we have for this in chemistry is bent. That's the name of the geometrical shape, bent. Okay, that seems really technical, right? Okay, you can laugh. It's okay. All right, bent. And this is the final molecular shape. Once you've gotten rid of all of the lone pairs, and you do it in the correct format, you're going to have a molecular shape. Once there's no more lone pairs in this step-by-step process, once there are no lone pairs left, you've got a molecular shape. Okay? So the first name, my baloney has a first name. That's bent. OSCAR. My baloney has a second name. It's MAYER. There's a second name, molecular shape. Okay? Y'all just remember I sang that for you, okay? All right? Look it up on YouTube. I'm sure it's on YouTube somewhere. Okay? All right? Oscar Mayer commercial. All right. It's famous. Okay. And again, this is actually, because of the lone pairs, this angle is slightly less than 109.5, but for us, we're not going to play with that too much. We're just going to assume all these angles to be 109.5. All right. You got it? You understand how the process works? Okay. Well, let's see if you do. I tell you what, do. Let's go make some models first. What do you say? You want to make some models first? Let's see what that actually looks like. So I've got back there on lab table 5 right now. What I want you to do is to get what you need from there and spread out at other lab tables. And everybody, well, let's say every 2 people. 2 people work together, okay? And make a model of this, all right? So you're going to have to find back there, and you're going to have to look around for this. You want a carbon atom. See if I know I've got one here somewhere. All right. Make sure you find a carbon atom that's got 4 equally spaced holes. Okay. And then you want to put 2 bonds on there. So in this modeling kit I have here, the bonds look like this. Now, some of those modeling kits back there, you have to put a hydrogen on there. Some already have the hydrogens on there. And this one I have to put hydrogens on there.
So we're playing with like Legos?
Kinda. All right. So that's the shape of the wall. Actually, you know what? This should not be a black one. That usually represents carbon. Let's put on a red one because that's usually what we use to represent oxygen, so you can see that. get the color coding right. All right, can you see how that looks like our molecular shape there? All right, so that's what it actually more or less looks like. And let me be careful to be clear about something, okay? The molecule itself can be pictured in a number of different ways. All right, this might be called a ball and stick model, okay, because it's got balls and sticks, okay? What this does not show is the actual shape of the overall molecule, because this shape does not take into account the electron clouds. The electron clouds are actually much bigger, okay? So the electron cloud on the hydrogen goes like out here, and the oxygen's out here, and when you end up with the actual shape of this, it's like you have three balloons, or three bubbles. You know, you've blown bubbles before and had them stick together? It's like three of them sticking together. Only what you end up with is, let me see here. So the actual shape of the molecule is something like this. And these would be where the hydrogens are, and this is where the oxygen is located. Okay? So once you take into account the electron cloud, you get that shape. But if you're just looking at how the atoms are linked together, that's what it looks like. Okay? Now everybody what I want you to do is to be able to see what this molecular shape is supposed to be. So build your model, come back to your desk, we'll start on something else. All right, time for you guys to do one on your own, okay? Or you can work with a partner. I'd like you to work, collaborate with a partner. And let's see if you can figure out using this system now, when we just talked about here, using this system, figure out the shape of a methane molecule. And methane is CH4. Just a reminder, because this is going to come up in the next unit, we're going to learn to name these things. Meth means one carbon. Ane means all single bonds between carbons, and we only have one carbon. We use that same suffix. Okay? So methane actually tells you the structure. So you do it with a collaborative learning partner, and then I'll come back and show you the way it should be done for you to compare it against, and then we can go build another model. All right, so let's move forward here with this. Let's see, carbon has 4 valence electrons. Okay, and it wants to have 8. That's called the Octet Rule. Atoms tend to want to have 8 electrons in their outermost energy level. The outermost energy level is called the valence level. And we're saying energy level and valence level, we're talking about the electron energy levels. And so hydrogens can combine just one time with something, okay? Once you combine with a hydrogen, no more bonding on that end of the molecule can happen. So in that respect, hydrogens are the terminators. Okay? Y'all didn't find that funny? Okay, I got you. Just saying. All right, so hydrogens can only bond one time. They can only share one electron. Carbon needs to share as many times as it can in order to get up to that 8 electrons. So far I've got 6 electrons for the carbon. This will be the 7th one, and each of these hydrogens are getting 1 extra electron. They're sharing one time to have 2 electrons. And finally I've reached the point where carbon has 8 electrons in its original form and with the sharing of combined, and the hydrogens all have 2 for 4 bonds altogether. So carbons need 4 bonds, always need 4 bonds. And the Lewis dot formula then is this. Okay? And then we want to find the shape when I put 4 sets of electrons around the central atom. Remember, sets are lone pairs, and also sets are all the electrons shared between any 2 atoms. So between carbon and hydrogen, that's a set. Between this carbon and that hydrogen, that's a set. 4 sets. The shape you get with 4 sets in 3 dimensions is a tetrahedral. And I want to put electron dots on each of those arms or angles. Okay. and that's a tetrahedral. And since all we have are electrons around it, we're going to call it an electron pair shape. The next thing to do is to redraw exactly that same drawing. But we're going to replace the sets of electrons in this drawing that are corresponding to shared electrons up here, replacing them with the symbol for the atom. And that's all four of these in this case. Now in our last set that we did, in our last drawing we did, at this point we would have had two more lone pairs left. Okay? In this case, there are no lone pairs left. And what I said earlier was, once we get to the point where there are no more lone pairs, then you've got a molecular shape. So this is the molecular shape. Okay? We're not even going to do a modified electron pair shape because we don't have a shape with both lone pairs like these two and atoms. Okay? So in this case, this is the molecular shape. And it has the same geometry as this, so it must be a tetrahedral. Okay? Alright, so you want to go back to that lab table again and find you a set of atoms in these models. Okay, now look, be careful. Carbons are usually represented by black things, but it doesn't have to be black necessarily. But you want to find a carbon atom or at least an atom back there that has 4 equally spaced holes for all your hydrogens, okay? And make the model, see what it looks like, and then return to your desk. Put everything back where you found it, and then return to your desk. Okay, I hope you all got something that looks like that. The critical thing is that these angles need to be all exactly the same. Okay? You need to be able to figure out in your head. And we're doing these in physical models, but once we do these in physical models, once we draw them on the paper, you need to be able to mentally translate what we draw on the paper to a mental image of something like this. Okay? You need to be able to see that that's not something that's flat. It actually represents something that's three-dimensional. Okay? It's going to help you a lot to do that. It's important that you learn to think three-dimensionally when we're only drawing things or looking at things that are two-dimensional. You've all done Rubik's Cubes, right? You know why Rubik's Cube was invented? Did I tell you that already? I did already? Okay. What? It was invented by a college physics professor to help his students think in 3 dimensions because it's that important. Okay? So he built a game, and of course he ended up making a lot of money in the process, all right? So let's do then ammonia. And that's NH3. By the way, you need to know when I say ammonia, you need to know that's NH3. That's just something you have to memorize. Okay, let's take a look at this then. Nitrogen has 5 valence electrons. Hydrogen has 1. So we're starting with the electron dot formula. I'm now making a sharing arrangement. And then I'm going to do a Lewis dot formula. So we've got 3 sets here that are all shared and 1 set that's not, for a total of 4 sets. That means I need a tetrahedral. So I've got a tetrahedral electron pair shape. And I need to replace 3 sets with a hydrogen. And this is still tetrahedral because there's 4 equally spaced angles here. But it's modified. A modified electron pair shape. So two names. Tetrahedral is the first name. That's telling us what the geometry is. Modified electron pair shape is the last name, even though there's 4 names in there. The point is that that's telling you which stage of drawing it is. And the last drawing then removes any lone pairs, but it's got to be the exact same shape. Now, this is the one that tends to trip students up. When they draw this, they tend to draw out something that's flat, and it's not flat. Okay? They think because I've got 3 hydrogens or because you've got 3 hydrogens on there, it must be 3 equally spaced angles, and it's not. Okay? When we do the molecular shape, this lone pair, which isn't shown, is actually taking up space and pushing the angles for these hydrogens down. Okay? So this is not flat. But it's not quite bent either, because bent is just 2 angles coming off the central atom. This is called a trigonal pyramidal. That's the geometry name. And since we don't have any lone pairs left, this must be the molecular shape. Okay? Now, when students are thinking about what this looks like in 3 dimensions, the reason for doing the models I ask you guys to do is so you can see what it actually looks like. The model isn't flat either. The model is bent like that. See how the legs are kind of bent down? And if I put it down flat, it kind of stands up into a 3-sided pyramid. You see that? 3-sided pyramid. You see the 3 corners of the pyramid? Everybody got that? Okay. So it's not going to be flat. And if you draw it flat, if you assume it's flat on a test or a quiz or something, you're going to be wrong. So I hope you took the time to make the right model back there, that you saw what the shape was going to be. Okay? If you're just kind of speeding through this stuff, that's my concern. That's why I ask you, some of you guys, are you sure you did this right? When you do it in a hurry, sometimes you miss the idea that I want you to get from it, that you need to get from it, not just me, that you imprint on your mind what the shape of this is going to be. Okay? That's important. All right. We're going to move now from these molecules that are very simple with only single bonds, only sp3 hybridization, to something that has a double bond. Okay? So let's do a molecule for formaldehyde. Same idea. I want you to do the find the Lewis dot formula, then find the 3-dimensional shape of this molecule. Okay? Being careful about what everything that's going together that I've told you so far. Okay? All right, so the first thing you want to do is find the sharing arrangement, which stems then from the electron dot formula. And when you put it together, you get this. Okay? So we've shared 4 electrons between the carbon and the oxygen. And we get something called a Lewis dot formula when we squeeze the electrons in between. So we have 4 electrons shared. It looks like the 4 corners of a box in between the 2 element symbols. Okay? And then we're going to take the sets of electrons around this atom that's governing the shape. Okay? Sometimes I call that the central molecule. In really large molecules, you don't really have a central molecule. You've got central atom. We don't really have a central atom in a large molecule. There's lots of atoms, and so each one of those centers have to be taken individually to figure out the shape of the big molecule. And you'll do that some in college, especially when you get to organic chemistry. But this is a simple molecule. We've got 3 sets here. Okay, all the electrons shared between any 2 atoms make up a set. So in this case, between this carbon and this hydrogen, I've got a set made up of 2. But in between this carbon and this oxygen, I've got a set made up of 4. So when I count all the sets, and there's no lone pairs here, when I count up all the sets, I've got 3 sets. So this is not going to be tetrahedral anymore. Okay, it's going to be flat, 3 corners, and that's called a trigonal planar electron pair shape. A trigonal planar electron pair shape. Okay? So I put the 3 sets equally spaced. Well, if I've got 3 things flat on the paper, equally spaced, what's the angle between each one of those bonds? What is the angle all the way around back to the beginning? 250. Oh, 360. I'm sorry, I misunderstood you. Okay, 360. So what's a third of it? What's a third of that? Huh? 360 divided by 3 is 120. So each of these angles 100. You can do this. This is not hard. 360. 3 divided by 3 is 1. 6 divided by 3 is 2. 0 divided by 3 is 0. So 360, okay, is divided by 3 and you get 120. Anyway, so there's 120 degrees between each of these angles. Okay, not 109.5 this time, 120 degrees, okay? And so from that then, we're going to get a molecular shape that's also trigonal planar. Okay? A molecular shape that's also trigonal planar. The thing to remember though is we took this set of 4 electrons and stuck 1 oxygen on here. So in all our balloon models, this bond would have looked a lot different, wouldn't it? It would have been, we would have had a single balloon down the middle, which represented our sigma bond, and then we had 2 balloons around the outside, or balloons looping above and below to make a pi bond. So it looked a lot different when we were making balloon models of bonds and lone pairs. Okay, the shape of the molecule doesn't reflect that. Balloon models, this molecule looked like that. Okay, but for the molecular shape, we only care about the angles between the atoms here and here. That makes sense? It's like we took this plate and flipped it up flat and more or less got that trigonal planar shape. All right, does that make sense to everybody? Okay. Now, this is where I want to bring in what's called a Lewis formula. Okay? In a Lewis dot formula, the electrons are pictured, okay, as 2 dots because we're sharing 2 electrons. In a Lewis formula, any shared pairs of electrons are replaced with lines. Okay? In a Lewis formula, any shared pairs of electrons are replaced with lines. So since there's a shared pair, 1 pair between this hydrogen and carbon, there's a single line here. Since there's 2 shared pairs between the carbon and the oxygen, there's 2 lines. Okay? So this is the formula that we're actually getting to in the end, but I usually do molecular shapes here using Lewis dot formulas because it's easier to figure out the angles that you're trying to work with. Okay, you could go to that, but I think it's easier to start with this, okay? Because I'm putting the sets of electrons on the ends of the arms like I have here. So when we do this shaped molecule, we're not going to be worried about that double bond as far as how it's shaping everything. However, in the molecular models you make, there is a double bond, but it doesn't look like the double bond in the balloon shapes we've done. It's just 2 of those little sticks going between the carbon and the oxygen. Okay? So when you make this model, you're going to look for a carbon, black carbon center, and you're going to find one that has 2 little holes really close to each other, and then you're going to find an oxygen with 2 little holes really close to each other to stick it on. Okay? You ready? Go back and see if you can figure out that model. So before we move on, let's be really clear. In the Lewis formula here, you still have to have the lone pairs on there. Now, the Lewis formula more closely represents the three-dimensional molecular shapes you're making from these modeling kits, okay? Because when you do a double bond, you have a bond that looks like this. That's not what a double bond actually looks like. When we were showing the shape of a double bond here in our balloon models, we saw there was a sigma bond in the middle directly on and surrounding a line between the two nuclei of the two atoms, and then a pi bond that was above and below, like this is the hot dog and this is the bun, okay? But this double bond in the modeling kits doesn't look like that. But you can see it's 120 degrees apart, just like in this drawing here, okay? What you're not showing here is the double bond, or the double bond. You got it? So they're telling you different things, or each kind of model is telling you something different. If what we really want to know is what is the shape of the molecule, then we care more about this than we do about this. If I want to know why it is that a protein in your body does what it does and forms the shape it forms, I care more about this and this than I do about this. But if I want to know how it is that I change this molecule and react it with something else, I care more about this because that double bond really impacts the way that the reaction takes place. So all these things tell you different things, and it's important to understand all of them to get the big picture, okay? There's a lot of dynamic stuff going on in the molecule shapes and our understanding of them that help us to be able to predict how things are going to happen or figure out why they're happening the way they're happening. Okay, so let's do the same sort of thing with hydrogen cyanide. Now, when you see cyanide, you need to be careful because cyanide, any cyanide compound is very poisonous. All right, so this is actually a very poisonous compound. We're not going to actually be using it in here. The formula for this is hydrogen, and Cn is what's called a polyatomic ion called cyanide. By the way, if you ever smell almonds and there are no almonds around, like nobody's made almond cookies or something, okay, I'd get out of there because that's the smell of cyanide.
Thanks, Mr. Tedder.
Okay, so for the past couple of days we've been doing balloon models to show the shape of molecules. So this is one for hydrogen cyanide, okay, and the triple bond is pictured like this big thing here in the middle. Somebody in my last class of the day figured out that this little part in the middle looks a lot like the beater you put on a mixer. You know what those look like? Okay, and it does. Okay, and the two red balloons here and here, okay, those represent one pi bond. The two blue balloons here represent another pi bond. So pi bonds actually come in two parts, and this balloon in the middle is a sigma bond in the triple bond. There's another sigma bond going out here to the hydrogen, and there's a lone pair back here on the back. Those are a little bit longer than I like for people to picture, but that's okay. All right, but now what we're looking at is no longer the shape of the bonds. We're more looking at or caring more about the shape of the molecule. Okay, and so that's what this system you're using now is going to get us to. So we're going to start with the electron dot formulas and sharing arrangement, and they get a Lewis dot formula. Okay, sort of a sideline to this is the Lewis formula. Triple bonds then, remember, any shared pairs of electrons become lines. A triple bond looks like this. Okay, now I flip this around. It doesn't really matter whether the nitrogen is on the right or the left, just to make that point. Okay, and so when we get the shape, then we get a linear electron pair shape because getting this set of electrons as far apart as I can from this set, well, 180 degrees is about as far as you can get. Okay, and so our molecule is going to be linear. Okay, and if you looked at that balloon model again, well, that's if you look at just where the atoms are located, okay, the hydrogen, carbon, and nitrogen are basically in a straight line. So if what we care about is the shape of the molecule itself, it's a straight line. You follow? Now the problem with the modeling kits that we have is those modeling kits really don't allow us to do triple bonds back there. The only modeling kit I have is one I have up here to allow me to show a triple bond, and it looks something like that. Okay, looks like some kind of strange spaceship, doesn't it? Okay, well, this is our triple bond here. Okay, it's just 3 of these little connectors stuck together, when we in fact know now from our balloon models that a triple bond has a sigma bond in between the 2 nuclei and a pi bond going around it this way, another pi bond going this way. It doesn't have this actual shape, but this shape does let us see that it creates a linear arrangement of all those atoms. Okay, and so this triple bond is a lot more akin to this triple bond picture in our Lewis formula. You follow that? Okay, so that's a linear molecular shape. Okay, all right. What I want to do is, I think you've all written down your homework already, haven't you? Okay, so there's one other assignment for you to do in the little bit of time we have left, and that is to find the shape of, using all this stuff, a combination of sulfur and chlorine. Okay, so this is class work to do right now. Determine the molecular shape, and let's name all the shapes while we're doing it to emphasize what the names of these 3-dimensional shapes are. Okay, so we're doing SCL in class now, then you're doing this one as homework, and then we reach the end pretty much of everything we're going to need to cover in this unit. So tomorrow then becomes our test preview day when we review everything in this unit, and then the test will be the day after that. So the day after tomorrow is the test for unit 3. Okay, so work on this right now. All right, I know that some of you are still kind of working on this, but because of time, I need to go ahead and give you the solution to this, okay? So we started with an electron dot formula, then a sharing arrangement to come up with a Lewis dot formula. Okay, that's the name of this, the Lewis dot formula. I didn't really ask you to do a Lewis formula, but I'm going to show you that in case you did. Okay, so the lone pairs still are shown on there, but single pairs of electrons that are shared, those shared pairs, those become single lines. The shape of this molecule, when we start doing that, we start with a tetrahedral electron pair shape because there are 4 sets of electrons around that central atom. Then we get a tetrahedral modified electron pair shape because we replace the 2 shared pairs with a symbol for the chlorines they're shared, this sulfur sharing with. And then we get rid of the lone pairs to come up with a bent molecular shape. So that's just like the same shape as the water molecule we started with when we started this lesson. Okay, everybody follow along what we're doing? Any questions about any of that? All right then. And you know your homework, you know what you got to do. Y'all have a good day. If you want some additional help with the shape of molecules, go to the class website, www.tetrachemistry.com. It's right here on this address bar here. Click all chemistry classes, scroll down to your chemistry class, and go to the instruction page. And then we'll go down to Unit 3. That's where we are right now, talking about molecular shapes. And there's Unit 3, and there is the unit text right there. It says just Unit 3 here on the left. Click that, and it's going to open up the text for this unit. Be patient. And there it comes. There we go. All right, so I'm going to scroll down here. And there's, in fact, everything you need to know for this unit is probably in this text. Everything you need to know for the test and such. So it's going to repeat a lot of the things we've gone over in our lessons. But you notice here we start to see where it's talking about molecular shape. Okay, and that's about page 139. Doesn't mean that this text, this particular handout has 139 pages. What it means is that up to this point there are 139 pages in all of the texts for all 3 units. And so Here are a couple of handout pages that help you by walking you through the step-by-step process to figure out those three-dimensional shapes, starting with the electron pair shape, which is in the left column. So starting with that, then we go to the right, and then you really only need these first 2 pages. There is some more here on a third page that will help you, but that's really all you need to be able to figure out molecular shapes for this class.